Today we'll be looking at convergence sequence with examples. We examine what it means for a sequence to converge and we'll find the limit of that sequence. So there are two definitions and the definitions are equivalent. A sequence Sn is said to converge to a real number x, that is the limit, if for any real number epsilon there exists a positive integer n of epsilon such that we have this equation, that is the sequence minus the limit when we find the absolute value will be less than the epsilon for every n greater than n of epsilon. So if this sequence converges to x, then x is the limit of the sequence. So we can use this to find the limit of the sequence or to show that the limit that is given is true. Then we write this as limit at n tends to infinity Sn, which is the limit of the sequence, is equals to x. Also, the equivalent definition is we have a sequence Sn, then we have another sequence An. The sequence of real numbers, and let x be an element of R, be a real number. If for some k greater than 0 and m a natural number, we have this Sn minus x less than or equals to k with absolute value of the second sequence An for this. If limit An is equals to 0, then this limit is the same as x. When we get to example, we'll understand this much more better. Example 1 and example 2 use definition 1, while the last example use definition 2. So we have to prove that limit 3n plus 1, limit of 3n plus 1 divided by 7n minus 4 is equals to 3 divided by 7. Note, this is at n tends to infinity. So going by definition 1, for each epsilon greater than 0, we need to produce n of epsilon such that 3n plus 1, 7n minus 4 minus 3 over 7, while this one represents the capital Sn and this one represents the small x, which represents the limit less than or equals to epsilon for this. So now we are looking for n of epsilon. If you simplify this further by finding the LCM, we arrive at this. If you simplify the numerator, we have 19 divided by 7 to 7n minus 1. Since n is a natural number, for any value of n greater than or equals to 1, the denominator will be positive and the numerator is already positive, which means that the whole of this expression will be positive for n greater than or equals to 1. Now, we seek an upper bound of the numerator and a lower bound of the denominator. But since the numerator is a real number, as you can see, the numerator is 19. So we don't need to seek any upper bound since it doesn't involve n. And we focus only on the denominator. So to get the lower bound of the denominator, we write the denominator as this. We don't need to bother about this 7. We are interested in the part that has n, 7n minus 4. So it's greater than or equals to kn because this is just a function of n. Suppose this n is n squared, this will be kn squared as well. So if we try k is equals to 3, now in picking the value of k, we have to be very careful. Then we have 7n minus 4 greater than or equals to 3n, which gives n greater than or equals to 1. When we simplify this inequality, we arrive at n greater than or equals to 1. It follows immediately that 3n plus 1 divided by 7n plus 4 minus 3 divided by 4 is less than or equal to 19 divided by 3n. From the expression, we have 19 as the numerator and we have 3n from this denominator, which is less than epsilon. This implies that n greater than epsilon. When we simplify this inequality and make n the subject of the formula, we arrive at this. Therefore, there are two n now, n greater than or equals to 1 and n greater than 19 divided by 3 epsilon. So n of epsilon will be maximum of this. We had one to this to be on a safe side, and we also add 1 to this, so which means that n of epsilon is equals to 2 comma 19 3 divided by 3 epsilon plus 1. So we can choose the maximum of this. So we go to the second example. Now from the first example, if 3 divided by 7 is not truly the limit, there will be a problem here. We will not be able to get the value of k that will suit this. But we will not go into that. Maybe that one will be for the next video. So this is proof that limit n squared plus 2n divided by n cubed minus 5 is equals to 0. Now, using the normal limit definition, we know that this is true. But in mathematics, we have to prove the reasons why it's true. So for every epsilon greater than 0, here we also use definition 1. Epsilon greater than 0, we find n of epsilon such that this, which is the sequence, minus, which is the limit 0, is this. So for n greater than or equals to 2, we find out that this will always be positive. So you can quickly look at it. The numerator will always be positive, no matter the value of n. Never forget that n is coming from the set of natural numbers. Then for n greater than or equals to 2, if we put 2 here, this is 8 minus 5, which means that the denominator is also positive. Now we keep this n is equals to 2 because you are looking for n of epsilon. Then for every large n, we want to know how large n is for this to be less than epsilon, because by our definition, this is what we are looking for. We want to see how less this will be, and we must be able to find n of epsilon that satisfy this condition. So because of the mess, what do we mean by the mess? We have two n squared plus 2 n here, and we have n cubed minus 5 here. So we have to find a way to simplify it more further. So as I said in the first example, we'll find some estimate, that is, we seek for the upper bound for the numerator and the lower bound for the denominator. And since the numerator is n squared plus 2n, it behaves like n squared for any large value of n. Also, so we denote it by bn squared. Similarly, we seek a lower bound for n cubed minus 5, which is the denominator, and it behaves like this when n is large. Then we denote it by this. So n squared plus 2n is less than or equals to bn squared. Never forget, we are looking for the upper bound, and it is written this way. So if we suppose that b is equals to 2, and we put 2 here, and we simplify this further, we get n greater than or equals to 2. Also for this, to get the upper bound here, it's supposed to be greater than or equals to, greater than or equals to, because we seek the lower bound. So if we suppose that, and if you take c to be 1 divided by 3, then n is greater than or equals to 2. Now we have n greater than or equals to 2, n greater than or equals to 2, and previously we have n greater than or equals to 2. So now for any n greater than or equals to 2, both condition on the numerator and denominator are satisfied. Suppose we have n greater than or equals to 3 here, and we have n greater than or equals to 2 here. We'll pick the maximum here. So, but since they are both 2 and 2, then we go with this. Then remember that this, we've assumed that b to be 2, which is 2n squared, and we've assumed that 6 should be 1 over 3, which is this. Then we have 6 divided by n. But remember that this is less than epsilon. If we put less than epsilon n and we make n the subject of the formula, we arrive at this. So this is accomplished by setting n of epsilon to be maximum. Since this is 2, we add 1 to it, and since this is 6 divided by epsilon, we also add 1 to it. But please do not forget that if this is 3, yes, we'll take 3. If this is 3 and this is 2, we take the maximum here for it to satisfy both conditions. So the last example show that the limit of this is equals to 1 divided by 5. Mere looking at it, we are sure that the limit is 1 over 5, but we have to show it that this is true in general. So for epsilon greater than 0, we need to produce n of epsilon such that this is less than epsilon for n greater than n of epsilon. Here, this is for definition 1, but here I will use definition 2. As we can see above, in definition 2, this is what we want to arrive at: xn minus x less than or equals to k of an where an is also a function, a sequence. So n squared minus 4n plus 2 divided by this minus 1 over 5 is this. When we simplify this, because of the absolute value, this can go away. Then we have this. Therefore, n greater than or equals to 1, this will definitely be positive. And we can easily see that by substituting 1 here, this will be positive. Substituting 1 here, this should also be positive. So from this now, we have to simplify this like the first, like the second example. So in doing that, it is easy to find an upper bound for the numerator. Why? Because this is negative. If this is positive, it will be a little bit difficult. So you can make reference to example 2 to see how to do that. But whenever the numerator is having negative here, it is very easy for us to reduce it to the dominating term, which is 20n. Now we need to find the lower bound for the denominator. So we want to have this is greater than cn squared because we are looking for the lower bound. Then we have this. Now suppose this negative 3 is plus 3. It will have been very easy like this, like that of the numerator. Suppose this one is plus. We don't need to write cn square again. We just take the dominating thing. But since this one is negative, so we have to follow this procedure. 5n squared minus 3 greater than or equals to this. So if we take c to be 2 and we simplify this, we have n greater than or equals to 1. Now remember that also we have n greater than or equals to 1 in the previous slide as well. So to simplify this further, we have 20n. This is for the numerator, and for the denominator, we have taken our c to be 2. Then we have 2n squared, which is 2 divided by n. Now in example 2, what we did was taking this one to be less than epsilon, but here, because of the definition in 2, it follows from that equation 3 above that k is equals to 2, these two, and we have a sequence which is 1 divided by n. So the limit of that sequence is 0, which means that it has satisfied the definition of equation 2. Therefore, the limit of this is equals to 1 over 5. Thank you very much for listening. If you have any question, you can drop it on the comment section.